Great. Any questions? Yes. I'm sorry? Yes. No, I don't remember anything, but I'll look. 7B. C. 7C, sure. Yes. Okay, what's your question? Okay, so let's see, what are we supposed to be doing here? So we're supposed to be able to do this without knowing what merge sort is. Let's see how true that is. So let's get some paper out here. So we have an array of length 16. And now we're supposed to be merging, so I guess we're starting out with merging things of length 2, right? So we're merging from 0 to 1. No, we're merging of length 1, I see. So I guess that's the smallest we can merge, eh? So we merge the interval at length 0 with the one at length 1. And now it's merged. So then we merge the one at length 1 with the one at length 2. And so we're going to have, how many of these merges? I guess 8, right? So we have 8 merges like this. And do we have 8? 1, 2, 3, 4, 5, 6, 7, 8. Yeah. Okay, so all of these merges here have, the intervals have length 1. Now we're merging this one here from 0 to 1 with the one from 2 to 3. Then we're merging the one from 4 to 5 with 6 to 7. And there are 2 more, right? So we have 4 merges of this ilk. Then we need more room on this page. Can I make it longer? No. Then we're merging, so now we're here, right? So that was 4 merges here. Then we're having 2 merges here. We are merging this thing from 0 to 7. No, I'm all wrong. We're having from 0 to 3 and 4 to 7. That's one merge, and the other one is then the one from 8 to 11 and from 12 to 15. So we have 2 merges like that. And then we have one final super merge from 0 to 7 to 8 to 15. So they have one like that. So over here what I have is the number of merges. And over here let me write down the length of each interval. So here the length is 1, here the length is 2, here the length is 4, and here the length is 8. So now let's say we didn't have 16 but 32 intervals, an array of length 32. Then probably of the length 1 we would need 16 of them. For length 2 we would need 8 of them, and so on. And so now you're going to have to eyeball and see, what are those 16 merges? Or in general, how do you compute the intervals? And I guess now you see the numbers, you say, well, it looks like I'm merging the one that starts with 0 with the one that starts as 1, and then I keep on going. So that seems like a simple enough thing to implement. What about the next time? Now the length has doubled, so how does one figure out the end of this interval? So that's a generally useful thing to know, that if you have an interval that starts at some value a and now it has some given length, then you know that the end is a plus length minus 1. So that tells you, now that you know that the length goes, 1, 2, 4, 8, that tells you where the end is. And then the next one probably goes from a plus length to a plus 2 times length minus 1. So those are the kind of things that I do on a sheet of paper to get going and to start understanding what the problem is. I always start with an example. I'm not smart enough to do it in abstraction. So if you're baffled by this problem, you have not drawn like this picture. So if you're baffled by the problem, have not drawn this picture, and nevertheless are able to figure it out, then you now know something about yourself, namely that you're smarter than me, which may or may not mean anything. But so you really want to draw the picture, you want to look at how the values develop. And so I want to leave you with that a little bit so that you can do that and then ask another question. Yes?
For the quiz, question 2.
Yes. Yes, thank you. So I had that on my list. Where's the quiz? That one was this one, and I have the question somewhere. Here. Yes, and that's a very good question. So the question was, so the selection sort algorithm has been working away for 5 iterations. And presumably what's an iteration here, I would imagine that's the loop where one, finds the minimum position and swaps. And we have an array of 10 elements. And now what must hold true? And so when you look at the options here, it talks about, do we have 5 more iterations or 4 more iterations, 5 or 4? Are they always necessary or may be needed? And so someone here put this question on Piazza, and it's a very good question, and said, look, in this situation here, where the rest of it is already sorted, it doesn't look like the other iterations are needed anymore. And so now one really has to think about what's the context of this question. The way I understood the question was that it talks about the selection sort algorithm as it exists in the book, and not like some version of the selection sort algorithm as it might exist. And now this algorithm, there's an essential difference between the selection sort algorithm and between you and me. If you or I look at this problem, now of course we eyeball the rest of the list and say, hey, it's already sorted, no point in going any further. But the selection sort algorithm is not a sentient being. It has no eyes. It can't eyeball. Right? The selection sort algorithm cannot simply look at the other 5 and say, hey, I'm done. So the selection sort algorithm has no choice. It must crank on and on and on and on for 4 more steps, and then it's finally done. We know it's for 4 more steps and not for 5 more steps, because when you look at the algorithm, it takes n minus 1 iterations over an array of length n. But unless we change the algorithm to add in another loop to check whether the tail is sorted, which is not the standard implementation, then it is going to keep on going. Now, it's an excellent question. Would it be a good idea to change the selection sort algorithm? Shall we change it so that before making yet another tedious step, that it goes through the rest of the array to check is it already sorted? Would it be a good idea? And I haven't really thought about it too much, but I don't think it would be, because the time involved in doing that checking is about the same as the time involved in finding the next max pause. Because the checking involves, is this array element less than that next one? Is this one less than the next one? Is this one less than the next one? And that when you do that, you might as well just go on and find the max pause instead of, making that checking as a separate step. So one might infinitesimally speed up the algorithm by doing something clever there, but it wouldn't really go into the big nature of it. So the question here is not, what might you do when you see this array, but what does the algorithm do? But I think it's an excellent question because it drives home the point that an algorithm is something that's completely dumb, right? It just follows the set of steps, whether appropriate or not. That's what the algorithm does. So I like that question. There was another question that I liked, and that was that thing with the big O, where someone, let me get this going here, where someone said, what is this, this order of growth thing, which one grows faster, which one grows slower? And so what I really liked is that this answer that one of you guys gave, where they went to Wolfram Alpha, which is really a nifty site, and plotted the curves. And so here you can see, which curve is faster than what. So here we see n cubed, which grows almost nothing. And now we have to, n log n grows almost nothing, right? Then there's n cubed over 2, there's n cubed, and then there is 2 to the n, which of course grows quite fast. So here one can really see which one of them grows. So is that cheating? No. Right? I mean, that's just like using an older generation, maybe my generation or the one that came after, would have used a graphing calculator. Now, does anyone still use a graphing calculator? No, right? I mean, that's a crazy thing to do. But, yeah. Except if you have to take 19th century calculus or some such thing. But, nowadays you use a site like this or some software like this to figure out the answers. And, if you have to do anything with math, I think Wolfram Alpha isn't bad. Other questions? Okay, I have another thing that's a little bit similar to what I was trying to get across with my answer to this question, and that is this whole do it by hand thing. So on the exam, the very first question, my intent was to see, can you do it by hand? Can you follow an algorithm and do what the algorithm does by hand? Why is it important to be able to do it by hand? What is the first law of programming? The first law of programming is if you can't do it by hand, you can't code it. It is impossible to code something up that you can't do by hand, except maybe in 46A, where the problems are so simple that you start up with some code and beat it into submission. But at this point, everything that you code, you have to be able to do it by hand. You have to be able to follow the steps exactly by hand. And I found it quite charming where some of the answers that I saw, it said, and so on. But that's exactly the point I was after, right? I wanted you to do the and so on by hand and drive it down to the final answer. So if you if you struggled with that one, by all means do it at home and do it by hand. And when you do that, there's one thing that I want you to pay particular attention to. Let me get a new page here. And that is when you read through the algorithm description. So here's the midterm. And so when you see this, what you see right now may be a little different than what you got on your individualized midterm, but they're all essentially the same question. So here the algorithm description talks very lovingly about corners C0 to CK, and then CK, Cn minus 1, C0. You see that here. And so, as you know from your discrete math class, if someone goes through the trouble of giving these things explicit names, like C0 to CK and CK to Cn minus 1, C0, these names are probably somewhat important, and when you draw your sketch, you don't just want to ignore them. So let me make the sketch here. So we had points 1, 1, 3, 1, And again, you might have a different selection of points. 3, 3. No, that's wrong. Yeah, it helps to draw coordinates. 3, 3, 1, 3. So, what's wrong about this diagram? Why is this diagram, as I just drew it, not going to help you solve this problem? Exactly. I don't know which of these is what, right? So I really have to say this one is C0, this one is C1, this is C2, this is C3, and this one is C4. That's crucial information. Without that, you're not going to be able to follow the algorithm. So when you see next time in a problem statement where someone lovingly named these things in particular ways, make sure to put that into the diagram as well. You know, at the beginning it's a cheap thrill, but we'll be grateful in just a second. Because now it says, you know, we need to find the two polygons that are constructed. Okay, here it says if n is odd, let's see what is n in our case. N is the number of points because we go from C0 to Cn minus 1. So n is 5 in our case. 5 is odd. Then the first one has one more corner than the second. And so it says here we're supposed to go from C0 to Ck. So that means we go C0, C1, C2, and C3 because the first one is one bigger. And so that is our first subdivision. And if you don't follow that, you could get some other subdivision, and then the numbers that you compute aren't quite the same that are expected. So you have to follow that verbatim. It gets worse. Now you have to say, all right, now in the smaller one, we have to subdivide it the same way. So this one here is the starting point of the smaller one, and so we have to go C0, C1, C2, and then the next subdivision goes this way, and it does not go the other diagonal. And I have spent an agonizing weekend tracing through 163 solutions like that. There are 14 possible different ways that the question could have come out. And so with each of you, I had to look at which question did you get, what were the points that you were actually supposed to have been getting. And so I'm glad that I finally slogged through that. But it is surprising that, you know, how many people did not follow it through to that level. So when I ask a question that says, can you do it by hand? I don't mean can you do some half-assed approximation of it by hand, but can you do the exact computation by hand down to the very last level of detail? And so that's important in many ways, and you're going to be, in a few weeks, you're going to be cursing a lab where you're going to have to be tracing nodes in a linked list or in a binary tree, and where I'm going to ask you to put every single memory reference on a sheet of paper and follow them all just so to find the bugs that are in there. And I know it's tedious work, but it is important that you can do that kind of tedious work. If you can't do it by hand, you can't code it. All right, that was the first one from the exam. The other one in the exam is where I'm right now spending lots of unhappy moments with, is to go through pseudocode. So I realize pseudocode is difficult. And in the first semester in CS 46A, pseudocode does not pay off all that much. Most of the computations are so simple that you might as well just write the 3 or 4 lines of code that are required, and the pseudocode doesn't really buy you a lot. And the other thing why pseudocode is hard in 46A is that if you don't yet know how to program, if you don't know what the basic rules are that you could say in pseudocode, then the pseudocode seems completely arbitrary. At least with programming, the compiler will help you along, but with pseudocode, you have to know some programming in order to make some use of it. So at this point, you do know some programming, and so you have a basic feel for what is reasonable to express in pseudocode as opposed to real code. And so now you have to learn some more rules about how to write good pseudocode. So here are 2 golden rules that I think if you followed those, you and if you check that with every line that you write, whether they fulfill those rules, your pseudocode would come out a lot better. So the first rule is, both of them are very simple and very straightforward. The first rule is that a pseudocode statement should map directly into either one Java statement or into a small number of Java statements. And that sounds pretty obvious. So a good example is ch is first character of stir. Right? That could mean stir.charadd of 0 or stir.substring of 0 and 1, depending on the context. And so here what we're saying is we don't really care about whether it's strings of length 1 or whether it's characters, but we know this is something that can be done with one line of Java code. We know it can be done with one line of Java code because in 46A we've done it with one line of Java code more often than we care to remember. Or here's another one. Set all elements of ARR to 0. Maybe there's some magic call, right? Isn't there arrays.fill or some such thing? Could be one line of code. Maybe you've never seen arrays.fill, then you can do a two-line loop, right? For I goes from 0, I less than ARR.length, I plus plus, ARR bracket I equals 0. 2 lines of code, set it all to 0. Straightforward mapping from the pseudocode to the Java code. The kind of thing that you expect every last student who passes 46A to be able to do in an instant. Now here's a bad one. So if it says break the input into strings in the other set, in one set, that's not what I meant to say. In one set and not in the other set. In one set and not in the other set. So here the pseudocode is not really helpful because it doesn't say how to do that. It doesn't say what Java statements would be necessary to do this. It's not at all clear what the strategy is to carry this thing out. And so then it's useless pseudocode because the whole point of pseudocode is to make these decisions right now in the pseudocode so that the decisions are done before coding. So the algorithmic questions need to be decided. They need to be decided before you get into code. Pseudocode is not there to give a high-level, general, managerial, director-level statement of what needs to be done. But it does have to say step, 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 just without the gory details of the minor Java thing. So when you look at the pseudocode that you have in your exam solution, for example, and if it's vague, if it's not prescriptive, then if it's not at the level where it could instantly map into 1 or 2 or 3 lines of Java, then it is bad pseudocode. The other important thing is when it comes to that translatability into Java, that translation has to be unambiguous. No choice, no algorithmically essential choice can be left to the user at the time. In other words, you should be able to debug your pseudocode. You should be able to have a set of numbers or whatever the inputs are of strings on a sheet of paper. You should be able to walk through the pseudocode, and if 2 people did that with your pseudocode, they should get the exact same flow of the algorithm. There should be 0 ambiguity in the pseudocode. So for example, good pseudocode, add C0 to the end of P. If you have whatever P is, an array or a list or a polygon, and you have C0 and you add it to the end, there's presumably only one way to add it to the end. Bad pseudocode would be add it to P because there may be multiple spots where it can be added. Good pseudocode here. K is n over 2 if n is even, or n plus 1 over 2 if n is odd. There are no 2 ways of interpreting that statement. Even though it's not technically formal Java, the ifs and stuff are inverted, and you kind of but it's perfectly good pseudocode. It's unambiguous. Here's bad pseudocode as I have seen it just for an hour this morning. Add the first half of the points to P. What's bad about it? You don't know what the first half is. You can only say what the first half is if the number of points is even, right? Then the first half is unambiguous. If the number of points is odd, there is an ambiguity. And from the problem statement, it's clear that there was this ambiguous situation because the problem statement made a big deal of what to do when n was odd. So if that point you say add the first half, then that means you're omitting an essential decision from the pseudocode. The pseudocode is not unambiguous. So, next time you write pseudocode, have a look at these two criteria. Does each of the statements in your pseudocode map to one or two or three Java statements? And does it so without leaving any implementation choice? That is the job of pseudocode, to tell you how to construct the Java, just getting rid of the repetitiveness and the boring part of public static void main and of for I equals 0, I less than blah blah blah. And so does it say how to make the Java out of it, and does it say so unambiguously? All right, it's very important to do that. Right now we're doing a lot of algorithmics, and in that pseudocode is really important. So I've Googled around in Stack Overflow to see if there was some tips to write good pseudocode. There's surprisingly little. There's some people on Stack Overflow who said, oh, I never write pseudocode. And that is true for some programmers. If what you do is write user interface screens, pseudocode is pretty useless. If what you do is write heavily algorithmic code, pseudocode is pretty useful because the algorithmics tend to be difficult. So it really depends on what you're doing when pseudocode is useful. Right now in this class, as it happens, pseudocode is pretty useful. So go do it. All right. Moving on to selection sort. So you've read how selection sort works. And I'm not even going to talk about that anymore. But I do want to ask one question. Why on earth do we care about sorting algorithms? And so this is something that when I first learned this, I said, this is the biggest waste of anyone's time, because if I ever had to sort something, if I, as a working programmer, had to sort something, how would I sort? How do you sort? You call collections.sort, right, or arrays.sort. No one in their right mind would re-implement the sort algorithm. That would be a crazy thing to do, right? Obviously, the people who've written collections.sort, they've spent a fair amount of time writing an algorithm that's as good and as fast as they can. So none of you, I hope, will ever implement selection sort from scratch. And the point of the teaching this is not for you to come up with better and better sorting algorithms. It's been done 50 years ago. No one does any research anymore on how to, well, probably someone somewhere, but maybe they do it on how to do it with a quantum computer. But this is something that's super well understood. Everyone knows what sorting algorithms are good and how fast they are. And so every practical programmer only calls the library sort and leaves it at that. And the library sort is not hard to understand. You don't need to know a lot about it to use it effectively. The reason that we do the sorting stuff is because it's like the first non-trivial algorithm where the naive way of doing it is much worse than the good way of doing it. With just about everything else that you've seen so far, the naive way of doing it, the straightforward kind of way, is about as good as the best way. But with sorting, that's not the case. And so one wants to drive home the point that there are algorithms out there where we're looking for the non-obvious improvement is really worth it. Everyone understands sorting. We've done it many times. And in fact, my poor wife has sorted all of your homework, all of your exam submissions. It took her 2 hours, by the way. I can tell you she didn't use merge sort. And so it's a well-understood problem, and it has this phenomenon that there is a non-obvious way of making it much faster than the obvious way. Selection sort is easy to understand, right? You go through this part of the array. You say, what is the smallest element that I can find? Let me look at this one where it's a little more obvious. So, the smallest part that you can find is 11. And you say, hey, by just putting it up front, I'm getting a larger part of my array sorted, and then I just keep on going. It'll obviously work. It's something that you might have done by hand. If you had a stack of papers, you just look for the next one in the remainder of the stack. You put it behind the already sorted stack, and that's the end of it. And it's not a very good algorithm. So here, and I timed this years ago, and you can see that if you have an array with 10,000 numbers, it takes less than a second. With 60,000 numbers, it takes 20 seconds. So that's kind of depressing. All right, so on this particular machine, I would like you to tell me how long does it take to sort 100,000 elements. I just want to know just how bad is this algorithm, this selection sort. So let me set up a clicker question. Okay, can you see the question, or why am I not getting any votes? No, it's open. Did I not post this? Ah, okay. All right, so looks like most people have figured this out. So C is in fact the right answer. And so what you need to do is, we were going to go to 100,000. So you go from 50,000 to 100,000. Now that multiplies it by 2. And as we've seen here, we know empirically that the time now goes up by 4. So 4 times 13 is, oh, I don't know, what choices are we getting? 52. Yeah, about 53 seconds. Okay, so that's how it goes. And so that's kind of bad. And let's see why that is so. So you've seen the math in the textbook that you need to figure out what are the number of visits. And so let me show that here. So in each iteration, you visit, well, in the first iteration here, you visit like n minus 1 elements. And here you visit n minus 2. And here you visit n minus 3, and so on. And you do this whole thing approximately n times. Now, the exact math is in the textbook, but the key observation is that you have n minus 1 plus n minus 2 and so on, and the formula that you need to remember in this game is that the sum of n and n minus 1 plus n minus 2, and so on, plus 2 plus 1, that's the same thing as n times n plus 1 over 2. And you just have to remember that. The way I remember the formula is that I just happen to know how to compute 1 plus 2 plus 3 plus 98 plus 99 plus 100. And the way you do that is you compute 1 plus 100, which is 101, plus 2 plus 99, which is 101, plus 3 plus 98, which is 101. And so that happens 50 times. And at this point now I say, okay, n is 100, so n over 2 is the 50, and the n plus 1 is the 101. And that way I know that I remembered the formula correctly. It happens often enough that I need to reconstruct it from memory, and there it is. All right, so the reason we get what's called quadratic performance is that we roughly do something n times, and each of which requires, on average, n over 2 lookups. So that's an easier way of thinking about it. Because, first you do n minus 1 lookups, then n minus 2, then n minus 3, and so on. And on average, that is n over 2. Half of them are longer than n over 2, half of them are shorter. And they're not exactly n over 2. It might be n over 2 minus 1 or n over 2 plus 1. But that's where the beauty of big O comes in. In big O, we say we only care about the growth behavior. We don't care about the exact nature of the equation. So this is something that is n times n over 2, or n squared over 2. And we don't even care about the over 2. We just say it's O of n squared. It's on the order of n squared. It grows like that. It doesn't grow like that. It doesn't grow like that. It grows like that. But not quite like that. So that's what n over what O of n squared means. There are many, many algorithms that are O of n squared. It's just life. And for some amount of time, people thought sorting is like that. That sorting just always requires O of n squared. To prepare for the next lesson, you're going to be learning an algorithm called insertion sort that I think I made you skip this time. And insertion sort is a different way of sorting that also requires O of n squared. The basic idea of insertion sort is that you have an array, and now you look at the first element, and now you say, okay, fine, this array is already sorted. Then you look at the second one, and so on, and eventually you have a sorted area and an unsorted area. And now you look at the first unsorted one, and you put it in here in the right spot. And if you keep on doing that, your array will be sorted, and it's O of n squared. So all of that is not very interesting. And I'm going to skip this one here. Oh, but I'm not going to skip this one. So before we go to a better sort algorithm, let's go to one that's worse. And so this is the algorithm that's known as the Albanian sort algorithm. Why is it called the Albanian sort algorithm? So you can't Google the answer. That's the only reason. So it's not actually called the Albanian sort algorithm, just for the purpose of this question. So here is a sorting algorithm that I now propose. You take an array, you randomly shuffle its elements, just by getting a random permutation. There's a call that gives you a random permutation. You just randomly permute the elements. Then you go and check, is it sorted? Is the zero element less than the first one less than the second less than the third less than the fourth, and so on. That is an O of n algorithm, because if you have an array of length n, it takes you n minus 1 comparisons to go all the way through. And I'll also tell you that to randomly shuffle the array, you can also do it in O of n times. But of course, you might not be so lucky, right? It was just a random permutation. So you keep on trying. Eventually, you will not be able to avoid the permutation that makes it sorted. And my question is, what is the complexity of this algorithm? All right, so let me set this up. All right, so everyone is taking discrete math or has taken it, right? How many permutations are there for the array? The length is n. What's the number of permutations? Okay, well, I hear n to the n. N, it's n factorial, yes. So there's n factorial permutations. And n factorial is n times n minus 1 times n minus 2 times and so on, right? Times 2 times 1. And so that means that this loop here, there's an implicit loop here in the if not repeat, right? So we're going to have to be doing this one n factorial times. Right? So that means that our complexity is going to be O of n times n factorial, because n factorial times we're doing n things. And now let's see if it is one of these. So let me turn off the hole here. So the slight majority answer was C, and D was the second most popular one. So let's have a look. So we have O of n times n times n minus 1 times n minus 2 times 2 times 1. Right. So that is more than O of 2 to the n, which would be O of 2 times 2 times 2 n times. And there's an n here. No, just like that. So because those numbers, are getting bigger than a 2, and there's, more than n of them, this one here can't be the right answer. This one clearly can't be the right answer. There's many, you have an n squared already in the first two, and lots of other numbers. What about O of n to the n? Well, that seems like it's going to be more, right? Because you have n times n times n times n times n. Now, admittedly, you could say you have a couple more, but they're just 2's and 1's, so they're constant. So it looks like that is less. And now there's a technical thing about what big O means. That means that actually 3 is the correct answer. And that is that big O is not very sensitive. Big O says whatever you put inside the big O is an upper bound. It doesn't have to be a precise or exact upper bound. That's why this theta is there for. But I mean, we're just in CS2, so we're not in 46b. We're not yet using the theta stuff. So big O is good enough. So for this technical reason, it is in fact O of n to the n, because n to the n is an upper bound. And so that's the right answer. So if you said 4 because you said, clearly O of n factorial should be different than O of n to the n, you're right. It should be different, and the mathematics of the O is just so that it's not. So we always intuitively use O as if it was that precise theta, but for whatever reason, that's the notation that we're using. So don't beat yourself up over that. But if you got either 3 or 4, you have the right answer. So some algorithms, are quite bad and take a long time. Of course, this is a stupid algorithm. But there are many, many situations in real life where even the best algorithms are quite bad. Where if you want to do certain kinds of optimizations, there are no known really good algorithms. So the lesson here is that big O is not just for sorting. So many students, when they first take 46b, they say, big O is just for boring stuff. It's for sorting where we know the answer. Later we'll see a few other examples with hash tables and stuff. But big O is for any time that you have some algorithm and you need to find out how good is it? What is the time involved as a first order of approximation? And so here I give you another algorithm just to make a big O calculation. You know the algorithm to find the largest value in an array. You have an array. You could look at the first element and say, is that the largest? And it is, because we've never seen another one. You look at the next one and say, is it larger than the largest that I've seen so far? Is this one larger? Is this one larger? Is this one larger? And so on. And you see this algorithm makes one pass through the array. If the array has n elements, it visits each of the elements once. And so therefore it's O of n. So finding the maximum is O of n. Finding the minimum is O of n. What about finding the median? Remember, the median is the element so that half of them are smaller and half of them are larger. And so hold that thought. We're going to later learn that that is also O of n, but it's not at all obvious. So let's look at another algorithm. I want to find the most frequent element. So I want to find the element that occurs more often than all others. So here's an example. I'm looking at this array here. And I say, what's the most frequent? Well, obviously it's 7. You have one look at the array and you know right away it's 7, right? So you'd say, well, that's O of nothing, right? You know the answer right away. But now imagine that there are thousands and thousands of values, and you still want to know what's the most frequent one. So at this point, you can't just look at it, right? Because you don't know what all those values are. So fine. So you could say, okay, I'm going to look at the 8. That's my first element. And then I'm going to count how often does the 8 occur. I'm going to go through the rest of the array and count. Then I go to the second element, and I see how many times does that occur. And if it was more frequent, then I forget about the 8. Then I just remember the 7 and how often it occurred. Then I'll go and look at the other 7 here. My algorithm is going to be stupid, and it's going to check again. Then it's going to look at the 5. Count how often the 5 occurs. So that's my algorithm. So for each element, count the tail, how often did it occur. If it occurred more often than the one that I had previously seen, remember it. So how do you compute this algorithm? So the big O of it. You say each time that you make a pass through this array to count how many 8s there are. Is this an 8? Is this an 8? Is this an 8? And so on. That's O of n. That's one lookup for every step. Now, how often do we do this? We do this once for every element. So we do n times O of n, or O of n squared. And so it is an O of n squared algorithm. And I'll come back to this at some point and ask, is there a better way? So big O is used for all sorts of algorithms, and it's used to find out approximately how much work is involved. Do you go once through the array? Do you go n squared times through, or something else? This is in fact where I'm after. So the algorithm that I've just presented seemed a little dumb. Imagine the array was sorted. Like that. Would it be easier to find out what's the most frequent element? That would be, right? Because you would first see what is the length of this segment. And to determine the length of a segment, you say, okay, I'll look at the next one, the next one, the next one, until they no longer are the same value. So you look at these ones here, and you say, oops, this is a 7, so the length here was 4. So you look at this one here, and keep counting, and you say, oh, there were 6 of them. So you can do that with one pass through the array. So if it was already sorted, you could find the most frequent element in O of one time, a single pass through the array. So now let's say we sorted. We only know one sorting algorithm so far, that's selection sort. So what is the big O efficiency by first sorting with selection sort and then finding what's called the longest run, the longest subsequence? So let's see. Selection sort is, oops, there it goes. Selection sort was O of what? O of n squared. And that algorithm where you make the linear lookup and you look at adjacent elements, it's O of 1. So there's a thing that I wrote up like this. It's O of 1. So if the array has n elements, and you keep looking at, this one, then this one, then this one, then this one, and so on to find the boundaries, you look at each element exactly once. Maybe you look at some elements twice, depending on how you set it up. Maybe you look at the ones on the boundary twice, because then you reset something. But so what? That would be 2n, and O of 2n is the same as O of n. So it is O of n. So what are the two together? It seems like, this should be the right answer. Let's see what people are saying. Okay, 80 people say O of n squared is the right answer. And those 80 people are actually right, because O of n squared plus n, O of n squared means it grows like this. O of n means it grows like this. And n squared plus n is essentially the same as n squared. I mean, it grows a little bit faster, but it's within the same order of growth. So the big O rules is if you have O of n to the 17th plus 1 million n to the 16, that you drop everything that's less than the highest power. Only the highest power counts, because that in the end is going to overwhelm the other growth. So the arithmetic in big O, as long as you only have polynomials, it's super easy. You just drop everything but the highest power. So O of n squared plus n, I guess technically it's not the wrong answer, but we always want to simplify to the best possible big O. So, if you said 2, you weren't wrong. And for that matter, of course, if you said 4, you weren't technically wrong either, right? Because O of n cubed is an upper bound. It's just not the best possible upper bound. But O of n squared is the answer that we would expect under polite people. All right. Why is it broken? That's my last slide? Wow. I thought I had some more slides. Okay. So I've been talking too fast. So, so next time what we'll be seeing is, of course, and don't leave, I'll talk a few more minutes about the homework then. So next time what you'll be seeing is a dramatically better sort algorithm. And keep that question in mind. What really is the best way of finding the most frequent element? That's not an unreasonable task, and we'll see several solutions during this class. All right, so let me since I've been wasting my perfectly good slides here, let me talk about a couple more things about the homework. So there was a question on Piazza where someone said, okay, they were having the following pseudocode for the Bulgarian sort algorithms, which I'm sure you've now all Googled. And so the pseudocode was like this. No, it's for I. I think that's a fair reflection of it. And it didn't work. And so what I wanted to show off is that you can debug pseudocode just fine in a situation like this. So I will continue to make you post pseudocode for this assignment. And so let's debug the pseudocode, okay? So we'll see what's I. So this is my array A. And I have I. And I starts out at 0. And so now we're going to be sorting this here. So what is the first call to 3 sort? So we sort these 3, so they stay at 149, right? So now I gets incremented to 1, and now we sort these 3 here. And so let me do that. So we have 1, 4, 7, 9, 2, 4, 6, 5. And then we sort these 3 here. And we get 1, 4, 2, 7, 9, 4, 6, 5. And so on. So the point that I'm trying to make here is that when you have your pseudocode, you can debug it. You need to have, that's what makes good pseudocode. If you can actually execute the algorithm on a sheet of paper, then you have good pseudocode. So if you go to Piazza and someone gives you pseudocode like this and it doesn't work, what answer can you put on Piazza? You can say, show me your program trace with the sample input. So when a student then produces, a series of transformations of what the input actually is transformed into under the algorithm, then you've put in a good answer and you've kept the other person busy and hopefully trying to do the things by hand. And so for these kinds of algorithms, that is a super useful thing to do. So next time, instead of asking someone, can you post better pseudocode or something, you should just say, do it by hand for one example. You might be nice and say, do it by hand for the specific example. And if you can eyeball their pseudocode and see where it goes wrong, you could give them an example where it goes wrong. And that would be a great answer on Piazza. So I would hope to see a few of them in the next few days. So whenever someone gives you bad pseudocode or pseudocode that's not working, don't just point out the mistake, but say, try it with this example, so that the student then can do that, do it by hand exercise. That's just really so important. So that's the one thing that I wanted to bring up. The other thing that I wanted to bring up is, what the heck is assert array equals? Where's that come from? So this is one of the functions that comes from, it actually comes from this thing here, from, what the heck's JUnit? What's JUnit? It's a test library that you've had, you had it right in the lab? Yeah, I looked at it. You had it in the lab. So lab 6 went through JUnit and unit testing. And so I was a little surprised to see a couple of questions on Piazza that said, what the heck is JUnit? JUnit is is really useful, and it's like the next level up from, you've seen these testers where we said print x, print expected 25. You know, you've seen these things in CodeCheck for several weeks, or if you've had 46A, for several months. And so these testers, where one just prints something and then prints expected, are like a baby version of JUnit. And so I've used them in 46A and 46B for a simple reason. That way you didn't have to add on an extra library. You didn't have to look for a separate set of API documentation. It just used what you already know how to know, namely printing. And it was completely transparent what happens. What's the disadvantage of this printing? When you have print this and then print the expected value. Why doesn't everyone do this? Why does everyone actually use JUnit? There's one huge disadvantage to these expected style testers where, you know, you print the expected, you print the expected, you print the expected. And that disadvantage is simply that if one of the calls that you're trying to debug, if it throws an exception, what happens? Yeah, your program is now dead and gone, and the other tests are not running. Whereas JUnit, if one of the test methods throws an exception, JUnit catches it and it keeps on chugging and calls the next and the next and the next. And so you get a much better way of finding out what your code does. The other thing is, sometimes you want to test whether one of your methods throws an exception. With my way of doing that, that is super tedious. The tester code has to try and catch the exception and print a message and print an expected message. With JUnit, you just put one of these annotations and say, in this call, I'm actually expecting this or that exception. So JUnit is better. JUnit has a whole bunch of other things that make testing generally easier. And just about everyone out there uses JUnit or some variation of JUnit for this kind of unit testing. So from now on, I will switch to JUnit for the CodeCheck things as well. And so should you. So you should, in your IDE, you should know how to get JUnit going, how to, run these tests, and that's what you had the lab for. So the lab had a very definite point to introduce you to what's state of the art in testing. And so the other point that the lab tried to make, and I've heard from the lab assistants that not everyone got that point, is that it's a really good idea to write some test cases before you even start implementing anything. There's some people who say you should write a whole lot of test cases, like 50 test cases, all the test cases ever, before you start writing a line of code. And I think that's too much, because it's boring. And if you want boring, you can become a divorce lawyer. So what you want to do is you want to write a few tests right away that you think, show off something interesting. One or two. I write one or two, and then I start coding, and then those tests pass, and I feel happy. And why do I feel happy? Because I see the green bar. Nothing makes me happier than seeing the green bar of JUnit. And so that's good, because that gets you into the dynamic where you test something and you're happy, and stuff works and you flow. Then what inevitably happens is something is not working. I see from the output of something that something is not working, but none of my test cases caught it. I now have 3 or 4 test cases already, but none of them caught that failure that I saw. Like I just saw an embarrassing failure in my solution to 7C. One of you sent me an email about it, and I just fixed it. And so then what you want to do is when you find your program failing, you want to go back and add another test case. Add it to the bottom of your 4 test cases that you already have, your 5th test case, and you run it, and you see it's red because, of course, you just noticed the error. Then you fix it. It's all green. You are happy. But every once in a while, what happens is you keep rerunning these test cases, and whammo, some of them turn red. Why? So why does it happen that you keep working on your code, and you just keep rerunning JUnit, that even though everything was green for a while, out of a sudden, 2 or 3 of them turn red. This is a very common phenomenon in testing, and the reason it happens is one didn't fully understand the problem, and so somehow one of the fixes to something reintroduced some error somewhere else. And it is a super common, that's the great advantage of having these test cases around. It's a cheap way of finding out that you've just made some mistake and then you can fix it right then and there. So this is something that people do all the time, and it is amazing how, as your code gets more complex, how common it is for an old test case to fail again. I'm involved in a project right now where we have about 300 test cases, and just this morning, several of them turned bad again that we thought we had fixed about a year ago. And we had fixed them, but the fix apparently was broken this morning when someone did something stupid. So this kind of testing is useful, and the reason to make testing successful is not to go overboard, but also to start doing it. So go ahead and start using JUnit in a way that you find effective. All right, that's enough for testing today, so I'll see you on Wednesday.